Another aspect of limits we need to consider is a possibility of vertical asymptotes. And so what we say here, suppose f of x is defined for x near a. Again, maybe f of x is not, or f of a is not defined. That's okay. The limit of f of x as x approaches a is plus or minus infinity, and you can write it this way. So the limit as x approaches a of f of x equals plus or minus infinity. If f of x gets arbitrarily large, and we mean that in the positive or the negative sense, the absolute value is getting arbitrarily large as x is arbitrarily close to a. So, and like we have in this picture, this time, as x gets closer to a from the left, this thing is getting larger and larger, right? So as we get closer, we would say here the limit as x approaches a from the left of whatever this curve is positive infinity. It's just going up. Now from the right, as I'm getting closer and closer to a, this guy is going down. So these function values are going down. So here we could say the limit as x approaches a from the right of f of x, this time is getting closer to negative infinity. So if you saw the last video, you saw that limits only exist if they match up from both directions. In this particular example, we're going to positive infinity one direction and negative infinity in the other, so the limit does not exist. Okay, so here, the limit of f of x as x approaches a here does not exist, dne. And that's, again, because these two limits don't match. It's a little bit different to wonder, well, what if they both went up? Does that count as a limit existing? Technically, by definition, it does. We talked about vertical asymptotes when we were mentioning the definition of a limit equaling infinity. And we can actually say a little bit more. In college algebra, you usually define a vertical asymptote as a place where the denominator equals 0 of a function. It's actually more than that. We can say that the function f of x has a vertical asymptote at x equals a if and only if one of the following is true. And when we say one, we actually mean at least one. Okay, so all of these could be true or more than one. That's okay. All right, so we could say that the limit as x approaches a from the left of f of x equals either plus or minus infinity, and I mean that it could either go to positive infinity or it could go to negative infinity. That's okay. That counts as a vertical asymptote. If I approach from the right, it goes to positive or negative infinity. And combining those two, if the limit itself is either positive or negative infinity, that counts as a vertical asymptote. So we could take a picture like this, and let's suppose here at 1, I know that coming from one side, it goes to positive infinity, and coming from the other side, it goes to positive infinity as well. Well then, by definition, I have a vertical asymptote here, and the vertical asymptote, remember, has the equation x equals a constant. So your vertical asymptote is x equals 1. Okay, let's look at this function 1 over x minus a. This is a common thing that shows up in calculus. It's a good thing to know. Some textbooks don't mention it, but I think it's very useful. So if I graph this thing, what this looks like is at a, so let's put a here, I have a vertical asymptote at a. And the graph of this looks like you have a horizontal asymptote at 0. And above a, you're going to do this thing where you kind of curve up, and below a, x below a, you kind of curve down. And so what we can point out here is if I'm looking at the limit as x approaches a from the left, just looking at the graph, we can see as I get closer to a this way, I'm going down. So this is going to be negative infinity. And if I take the limit as x approaches a from the right, 1 over x minus a, you can see as I'm getting closer to a from this direction, it's going to go up. So I have a limit at positive infinity. Okay, so we can use this information to solve a lot of limit questions, like the example I'm about to show you. So using the the previous theorem, we can address a question like this. It says find the limit as x approaches -3 from the right of x plus 2 over x plus 3. You learn later on that I can actually break this up into a product of two limits, where I can say the limit as x approaches -3 from the right of x plus 2, the numerator, times the limit as x approaches -3 from the right of 1 over x plus 3. And then I'm allowed to evaluate each of these portions themselves. Okay, so x plus 2 is just a line, so it would be something like this. So as I'm getting close to -3, all I have to do is plug in -3 into my function, and I see that that's going to be -1. Now, the second part, it may be useful to think of 1 over x plus 3 as 1 over x minus a -3. And so, remember, as the limit as x approaches a from the right of 1 over x minus a, we saw that that goes to positive infinity. So I know that this function here, as x approaches -3 from the right, we're going to go to positive infinity. So you can think -1 times values that are arbitrarily large, we go into the negative direction. So there's my answer. I hope these make sense. This theorem here is very useful. It shows up a lot. Commit it to memory. If you have any questions, I'd be glad to help. Just please let me know. Thanks for watching.